Good afternoon, good evening to everyone. To today's session of TUMIVolt Charging Station series. Today we'll be speaking on the topic of software-based planning of e-bus projects. So this webinar is being organized under the project TUMIVolt under the Transformative Urban Mobility Initiative, and it is being funded by the Federal Ministry of Economic Cooperation and Development, Germany. And yeah, maybe we can move to the next slide. Yes, so I'll just quickly run you all through the house rules for today's webinar session. So we will request all the participants to keep their camera and microphone off. Kindly consider to write your questions or even technical queries in case if you face any into the chat box, and we will take up your questions at the end of the session. So I would also like to inform you that this webinar session is being recorded and it will be uploaded on YouTube channel of TUMI, as well as on the TUMI website for further dissemination in a day or two. So the agenda of today's session will be a brief introduction about what we will be talking on, introduction about our expert speaker and the moderators. The second main agenda point today is the expert presentation on the topic by eBus Plan. And lastly, we'll be taking up the Q&A session. So we will request all of you to kindly write your questions, and even during the session, if you have any questions, please consider to write them into the chat, and we will take it up later after the end of presentation. So today we will be speaking on the topic of software-based planning of e-bus projects, where we intend to discuss some burning questions on the topic of how to plan electric bus projects, how to select maybe the right concepts and optimize charging solutions for electric bus projects. Should it be only battery electric buses, or should it be the trolley buses, or maybe the fuel cell buses? How to select these things or these project concepts using software-based planning tools? How to compare the total cost of ownership of the different project concepts, not just with the technical considerations, but also considering the operational aspect. And does digital services, use of digital services or the electric bus project make economic sense? And finally, we'll be speaking on discussing on how to optimize the operations and control once the electric bus projects are implemented. So today we have with us Mr. Philip Sinhuber from eBus Plan. Mr. Philip Sinhuber is co-founder and managing director of eBus Plan. His background is on electrochemical energy conversion and storage systems, and he is active in the field of electric bus research and development since 2009. He co-founded eBus Plan in 2015, and since then he has provided expert advice on the electrification of the bus fleet for several bus operators as well as cities in Europe and the USA. So a very warm welcome to our speaker, Mr. Philip Sinhuber. It's a pleasure to have you today. And today's session will be moderated by myself. I'm Rohan Modi, and I'm working as an advisor with the project TUMIVolt at GIZ. and my colleague Marvin Stolz. He will be taking up the Q&A session at the end of the presentation. So once again, I would like to welcome you all, and without further ado, I would like to hand over the screen to our speaker, Mr. Sinhuba. Mr. Sinhuba, the screen is yours.
Yeah, thank you very much. Thank you very much just for the very kind introduction, and now I hope that you can see my screen.
Yes.
Perfect. Yeah, I would also like to say hello and welcome everybody. Thank you for joining, and of course, thank you very much for TUMIVolt to give me the opportunity to speak here on the topic of software-based planning of electric bus projects. Yeah, I will then would like to start with a little introduction of eBusPlan as a company. Somebody already said a lot, but about our company and the background, I wanted to add that yeah, we are planning and implementation experts in the field of electric buses with a strong background in battery systems and fuel cell systems and engineering there. We have developed electric buses, battery buses, and fuel cell hybrid buses in the past, in our time at the university, and we have developed towards operations and to answering the questions how to best fit in the technology in operations. And therefore, we have developed simulation and optimization methods that aims at bringing together the technical constraints and the operational requirements regarding vehicle scheduling blocks and so on. And I will come to speak to this later. So we develop tailor-made concepts for technology and operations for our customers by carrying out feasibility studies, by designing the infrastructure and planning the infrastructure, charging infrastructure and so on. But we also write specifications, technical specifications for tender calls and support our customers in the procurement process, which is usually a public procurement process most often, and provide expert advice on different topics such as battery and fuel cell systems. And here you can see a little list on of our customers. As has been already said, we are working mainly in Europe and in the United States so far, and we provide, for example, expert advice to the bus operator STIP in Brussels. But we've also been active for Transport for West Midlands in Birmingham, in England. We have developed the electrification concept for the entire bus fleet of Vienna in Austria for Wiener Linien, the bus operator there. And currently we look at the electrification of the double-deck buses for the bus operator in Berlin, BVG, which is also a very exciting project. And yeah, that's a little run through what we do, who we are, and now I would like to come to speak to the main topics. And I would like to start with a little run through the processes at the bus operators, or well, let's keep it more general, from service design to implementation of bus services. It usually starts with the needs assessments. Where are my passengers? Where do they need to go? And the development of a local transport plan. And then we know the itineraries, but basically we know the frequencies, but we still need to develop the timetables to have the concrete journeys, the trips, which usually also looks at the interconnections and so on. And then we have the sum of the trips that the bus operator needs to deliver, the services that the bus operator has to deliver, the concrete, and then yeah, it comes to operations planning, which is then basically the scheduling of duties of driver of driver duties and of the vehicles to derive then the duties and the shifts and the blocks. And then next step would be then would get more and more towards the everyday operation between the delivery of the services, the implementation, and that's what I've called here operations. So the dispatching in the depot, maybe with the depot management system, and the fleet control, then operation steering when the buses are out to monitor the delay or if there are any disturbances there. And now we can say, we can divide it roughly as shown here. We can say that the upper part, now when it comes to the transition of the bus services to electric bus operation, then the upper part would probably not be affected that much by electric buses. No one would really, I haven't really met anyone who is considering to change the itinerary or the frequencies just to accommodate electric buses. This would be designed according to the demand. But the vehicle scheduling, dispatching, and fleet control is strongly affected by e-buses and their additional constraints. The additional constraints being then limited driving range, battery capacity, and also the need to recharge at the end of the day or during the day. These are the most prevalent or the most easy to see constraints that electric buses then bring along. So let me focus on this on the lower part here on from planning to operations, and look at the challenges that electric buses bring along to the existing procedures. And there I would like to focus on vehicle scheduling first. Well, now with vehicle scheduling, I mean the planning of the deployment of the vehicles, of the buses, by sequencing the trips. The blue blocks here, for example, are the blue bars are the trips, and then together they form such blocks. And in between these several blocks, there are charging phases here in the case of electric buses. In the case of conventional buses, then there would be no charging phases in between, and the blocks could be longer because of the driving range, of a longer driving range. But the aim of this all is the aim of this planning is to minimize the PVR, the peak vehicle requirement, so the number of buses that are required to deliver the services, and the deadheading, of course, which is unproductive mileage, which is just as expenses, and the driver costs, of course. This is what the optimization then aims to minimize. Now what we see very often is that a very simple vehicle scheduling approach is taken. So that means that basically the length of such a block is limited to a certain number, be it 150 or 200 kilometers, and it's not really by the energy consumption and by the battery capacity, but just simply by limiting the block length. And then the second point is the charging time. Buses need to recharge during the day, and in the example, or at least in the example here, they could not go the entire day without recharging in between. And in this scenario with depot charging, the buses would recharge here, and these are these yellow charging phases. And when we go with a very simplified approach, we simply say we reserve a certain amount of minutes at the depot to recharge. Then, of course, this will be a conservative approach, and the actual charging phases will take shorter, and that means that we lose efficiency and we over-dimension everything. And now on the right-hand side, there will be an example for what we called energy-based scheduling, or the results of an energy-based scheduling. You see here the implementation plan, the vehicle schedules, the blocks and the bus runs for exactly the same scenario, but with now, so the blue bars are the same as in the left-hand side, but they are arranged in different way. And now, in this case, we have predicted the actual energy consumption for each trip, for each standstill, for each block, and have rearranged it accordingly, and you designed the blocks accordingly, and also insert the charging phases using a charging time prediction, so that we only need to recharge what was actually consumed, and so we can optimize it by considering energy consumption and charging time, and therefore we end up at 3 vehicles that we can save. Here you see it's 20, and formerly it was 23 vehicles. So basically, it increases our efficiency. And to do this, we need a consumption model, of course. We need to forecast the energy consumption, and we also need a charging model that models the charging behavior of the batteries to predict the charging time. And this is what is then required for this optimization of operations. Now that was vehicle scheduling. I would like to also have a look at the dispatching, which is probably part of an entire depot management system. What this usually does is to assign the specific vehicles to specific parking positions and specific blocks, probably one day ahead. And then, of course, during the day, during operations, it would monitor and readjust these assignments. So if a bus has a delay and returns to the depot with a delay, then probably another bus needs to be sent out. Or if a bus is, for some reason, if a bus is not ready, then the dispatcher needs to send out another bus to cope with this. Very often it is done rather spontaneously. So during the day, it is decided which bus will go on which service, on which block. And now with electric buses, of course, and the need to recharge, there come additional constraints. For example, when assigning a vehicle to a parking position, this also means that we assign the vehicle to a certain specific charging station. And when we assign a vehicle to a block, then we need to make sure that it will have sufficient state of charge to be able to go on the block, on the upcoming block, which will require a certain energy, of course, a certain level of state of charge, the SOC here. And of course, and then that's also in the question of the charging station. If we need to make sure that there will be sufficient time to recharge the bus so it can go on the next block with a sufficient state of charge. And at this point, then again, it is obvious that we need an energy consumption prediction to do the dispatching, and also a charging time prediction. And that requires, again, models for consumption and for the charging behavior. Now, looking at the fleet control, what this does then is basically to monitor operations and to take certain measures to compensate for disruptions, for disturbances of the operations. And now with electric buses, of course, there are additional challenges there. We need to monitor range. This can be done, for example, in such views here, user interfaces, where the dispatcher can see when the color of the trips will turn red and when there will be critical from state of charge, and if he needs to do something like send out another bus or try to arrange some whatever charging scenario. And then it's also we also need to assess the consequences of such dispositive measures. So, for example, to send out another bus, or to have a bus that's somewhere else to come and continue the bus service, the services of the first bus who ran out of energy, for example. And before taking such decisions, we need to assess the consequences for the rest of the operations and for charging strategy and for the other buses. Therefore, we need to again need to have an energy consumption prediction and a charging time prediction. So at least when it comes to charging at terminal stops during operation during the day, also called opportunity charging. So this is this again requires then, as you might have guessed now, the prediction of the consumption using models and also for the charging time. Now, there's one more thing that is new with electric buses that is required now, and that's charging management. We need to control the charging phases and plan the charging phases. And I want to take a look at this one. Usually the dispatching, when assigning a certain vehicle to a certain bus position or a certain block, so when this decision is taken, that means that it generates a charging request, because it means nothing else than the fact that this vehicle needs to be charged to a sufficient state of charge at the charging station where it is assigned to until the departure time. So that's what I call the charging request then. And what the charging management does now is to convert or translate these charging requests to charging plans, so to concrete power profiles that will then be communicated usually via OCPP, charge point protocol, to the charging stations so that they can then charge the vehicle accordingly and to monitor charging the progress and infrastructure availability. That's also, of course, one job of the charging management system. Again, we need maybe not an energy consumption prediction here, because the target state of charge is already set by the dispatching, but still we need to have a prediction of the charging time to make sure that of the charging behavior, so that we can efficiently plan the charging of the vehicles and, for example, do such things like peak shaving here, so to postpone charging events when there is sufficient time, and to minimize the power drawn from the electricity grid and such tasks. And so all in all, again, we need certain technical representation or model of the technical constraints. So we've seen that we basically need a model for the energy consumption and also for the charging behavior in all of these steps. And now, of course, all of these steps could be carried out by different systems, by different software systems. Sometimes the one is done manually with on paper, on Excel, or in other particular larger depots, it's done more automated. However, of course, it makes sense now to use the same prognosis and the same forecast for all these different steps to make sure there are no conflicts between, for example, dispatching and fleet control. If the dispatcher sends out the vehicle and says, yeah, it has sufficient state of charge, but the fleet control says, no, it won't be able to go until the end of the day, end of the service, then there's a conflict that needs to be solved somehow. And yeah, that's why these two blocks here need to be integrated deeply into the structure. And then there is an additional a planning phase, or a different, let's call it planning phase, that is important, and that's the development of a conversion strategy from conventional buses to electric buses. And that's what I've called the system design. So the question, which concept is the right one? What battery capacities do we need? Where do we need to recharge? Is it in the depot, or maybe also in the charging hubs in the city? What infrastructure do we need? So what charging power, and how many chargers, actually, how many charging stations do we need? And there, of course, the question how to integrate the charging phases into the operation scheme. So the planning of the vehicle scheduling and charging scheduling is, of course, important here, design factor. And Now it's very obvious, but I want to show it once more with an example how the battery size can impact the efficiency of operations. You can see here on the left-hand side the smaller battery, and you see here the again the different trips over the daytime. And you see that here with basically this scenario with a smaller battery, the buses can go 3 trips in a sequence in a row and then need to go back to the depot. These light blue blocks here are pull in trips then and pull out trips. And then they need to recharge here during the day and they go out again later on. And all in all, we need 48 buses to deliver the services. And looking here at the larger battery, we can go 4 trips in a row before the bus runs out of energy and needs to be recharged again in the depot. And that enables us to really, for exactly the same trips, we need 8 fewer buses, 8 buses less. And that's, of course, an enormous increase in efficiency and in costs at the end of the day. So that's very simple. Larger battery, longer bus runs, fewer vehicles required. But the same is also true for the charging power, so the dimensioning the charging in the depot. If you look here on the left-hand side, you see the operation scheme with 150 kilowatt of charging power with comparably long charging phases, the yellow ones here. And we end up at 24 vehicles here in total. And on the right-hand side, with a higher charging power of 450 kilowatt, we have we need less time to recharge, so less unproductive time in the depot, and we can do the same services with 20 vehicles only. So higher charging powers here also can lead to fewer vehicles and to increase in efficiency. Now you can imagine there's a variety of, or you probably know that there's a variety of different configurations, charging power levels, battery concepts, heating concepts, and of course, we always have to answer the questions regarding the energy demand, which is not a constant, but it will depend on your operation scheme, of course, and the dwell times and the heating demand and many different factors, but also the need for charging infrastructure and the depot or terminal stops, the number of vehicles required to deliver the services, additional overhead, and so on. And all this, our experiences show that this varies greatly from company to company. And that is why we need to analyze and compare many scenarios to find the best suited concept that fits best to the local constraints and to the local requirements. And we do this by applying our software-based planning process. So we have a basically model of all the trips that we read in through standardized, all the trips that were planned, and we read in through standardized interfaces to the software systems at the bus operators. And we have technical models to simulate operation. We can model then potential charging locations and charging strategies, and then we can take the given vehicle schedules, bus runs, the blocks for as they are right now, and then optimize the technical specifications, battery size, charging locations, charging power, and so on, but also in the other way around, to optimize vehicle schedules for given technical specifications. So if we have a set battery size, then we can analyze how many vehicles do we need. If we recharge at one terminal stop or on both, how does this translate to the vehicle requirement, to operational efficiency? That's the operation concept then, and we basically need both to find the right suited, the best suited solution then. As use cases, there are different use cases. Think about that, how this could contribute to the overall system design and support the entire process. And this is the one, of course, to first of all to select bus lines and line bundles to be electrified first, maybe, where it is more easy to operate electric buses on, where we need less infrastructure, for example, to start with the conversion process. And so we can assess then, as I've shown before, by comparing different scenarios, where it makes sense to recharge, which technology choice makes the most sense. And then, for example, for each bus line that is shown here, identify the number of vehicles that we need for different electric bus concepts. So here, each line is one bus route, one bus line. And you see the number of conventional buses required to provide the services, the route services. And here you see the number of additional buses. And you see here for depot charging, for example, of type 1 with a certain heating concept, it requires 2 additional buses. So in total, it's 9. And when we have a different heating concept here, it would require no additional buses. So 7 plus 0, we stay at the same number as the diesel buses. And there is also opportunity charging concepts evaluated here. This is how you can then, by really calculating through these scenarios, analyze which concept makes most sense and develop the concept. And once you have done this, once you have put together the infrastructure options where you can recharge, and how you can operate the buses and plan the operations and the technical designs, battery size, charging power, and so on. And you quantify the number of vehicles, the infrastructure, and the additional operating expenses. You then can take this as basis for a TCO comparison, the total cost of ownership comparison, considering then vehicle procurements, operating costs, personnel costs, infrastructure, and so on. But you can also, because you know then the energy consumption and you can then calculate the emission reduction potentials and then compare the different scenarios in terms of costs and benefits, emission reductions. And you can compare all the different options and configurations then and select the best suited technology and define your build-out targets. Then also when it comes to the procurement, then you have made your concept and decided you want to have this battery, this vehicle configuration with this charging strategy. You can then design the tender specifications identify then, of course, battery size and charging power as the very simplest approach here, which will then can also be used then the scenario analysis to evaluate different bids. So usually it's a public procurement, and you will have different bus manufacturers and infrastructure suppliers to hand in offers, and with different battery sizes, different charging configurations and charging power and efficiencies. And now you can, by calculating through these scenarios, you can then check the technical feasibility, buffer, and stability of the different offerings of the industry, and then also calculate the operational expenses and the follow-up costs, then energy consumption, the efficiency of operations, which is not, of course, directly visible, is not directly transparent when you get a offer from a bus supplier. Then then of course you can use the tool in the scenario calculation to analyze such set of charge profiles as shown here. So if you have the bus run and with a different journey, you can you can simulate the energy consumption and know then, and then also the recharging phases. Here now it's an opportunity charging concept at the terminal stops. You see that the state of charge is the solid red black curve is going up and down when its energy is consumed, and energy is recharged during the day. And the dashed curve here is the worst case scenario with an aged battery and high energy demand, you can see that it is still feasible, this bus run, this operation scheme, but you could identify then optimization potentials, room for improvements, and dimension buffers. So it's really required to look then at such questions, of course, to make sure that the system design then fits well to operations, and the implementing or the introduction of electric buses will work actually. And then, of course, once you have done this in a simulation, then you can calculate such scenarios where you to evaluate the infrastructure, demand, number of chargers, but also the important thing then the dimensioning of the electricity network connection. You see here in our software, for example, for a load profile here. So it's power drawn from the electricity network over the day here, or the time of the day, and you see the amount of energy drawn from the grid, which then can be the basis for the procurement of the energy procurement and the energy procurement strategy. So again, here scenario calculation and you could lead to deriving the right planning basis for discussions with other parties, like the electricity network operator, for example. Yeah, that's basically it. So now I'm around about 30 minutes, and I'm about to wrap up and conclude. So we see that electric buses bring along additional complexity for planning and implementation of bus services, and these are the technical constraints. For example, the battery behavior in terms of capacity and charging behavior, the energy consumption, of course, of the vehicle, and which then together gives you a limited driving range that needs to be considered. And also the charging technology, which will also, of course, impact the charging time and therefore efficiency of operations. And yeah, the entire delivery chain, the entire chain of the delivery of the bus services is affected from the planning on to the fleet control and charging management. Of course, as an additional component. Then, however, we can approach these challenges using technical models for the energy consumption and also for the charging behavior, and we could during the time using log data to improve these models, to use, for example, machine learning algorithms to improve the energy consumption forecast and the charging time forecast, and make it even more precise and optimize operations. And third bullet that I wanted to mention is that upfront there is a need to design the system in a way that you can optimize the operations and the total cost of ownership, and therefore, so that's what we call strategic system design, and therefore we need to analyze and model the current operations, adjust it, see which bus concept translates to which operational efficiency and costs actually then, and then this scenario calculation enables us to make transparent the different interdependencies and to find a good decision basis there. That's what I wanted to say. Yeah, thank you very much for your for attending here, and I look forward to your questions and the following up discussion now. Thank you very much.
Thank you very much, Mr. Zinhuber, for this very comprehensive overview and for the presentation. I'll just quickly share my screen to also kick off the last agenda point, which would be the Q&A session. So to all the participants now, of course, you are more than welcome and invited to write your questions into the chat, and I would then redirect them to Mr. Zinhuber. We've received a couple of questions, and we also have some questions ourselves. But maybe let me start you with the first one. So someone of the audience asked, during planning, the focus is on retaining the existing diesel bus schedule and bus allocations, or would you suggest re-engineering the entire block scheduling and also the bus assignments? And just to, there's another comment on this from the same person. He sees mostly diesel bus plans as given, and trying to follow those diesel bus assignments for e-buses. Thank you.
Yeah, I think it's a very good question, and this is exactly what we wanted to address. So far, we have seen that when it comes to at least to battery buses, then in many cases we need to adjust the schedules, but it does not necessarily mean that we mix them up totally, and change everything. I would say that you would have to look into details there and see if it makes sense to, if maybe most of the schedules can be maintained as they are, if the batteries would not run out of energy, if they can be recharged, for example, then it could make sense to maintain them and only adjust a few blocks that are too long. But in many cases, I would say it makes highly sense to adjust and to think a bit more, to not stick too close to these. I know that many bus operators back off doing this because it means a lot of efforts there, but it could be worth doing this if you then can optimize operations for the electric buses. And so I would say in not every case it makes sense, but in many cases, yes.
Thank you. Perfect. And maybe a follow-up question regarding the software you described during the presentation. Just a short question: is the software proprietary? Sorry, is it a software just for your company, or is it also available for others to use, for example, consulting services?
It is also available for others to use it, also probably also in consultancy services. We are currently trialing it with a few bus operators, so it's already in use at a few bus operators within this project that we have mentioned, Strategie E. So it's really designed to be used not only by ourselves but also by others who are with a minimum level of understanding, of course, of this. But I think it's really simplifying this, and that's the aim basically of the software, to be also deployed by others.
Okay, great, thank you. And maybe also a question from my side. From your experience advising different cities around the world, what are the biggest challenges when advising them on the implementation of e-buses, and where do you have to do the most, I don't know, persuasion work, or where do you have to go into detail the most? Would be interesting to know.
Yeah, that's a good question, because you could have these big issues on different levels, be it the structure and the processes at the bus operator, be it the fact that very often knowledge about the technology and about the peculiarities of electric buses is not spread evenly across the operator, but is limited to some experts. Then also time to time have a hard time in providing guidance to the entire company on this road to electric bus operation. And of course, we don't really, we are a technology open, and we don't, we provide neutral consultancy services there, so that we're not the ones who sell electric buses to the bus operators, but we make very transparent in a neutral way the costs, the impacts on operations, and the different factors, the infrastructure needs, and then provide them a decision basis for them. But I would say that most often when comparing the different technologies, the operational impacts are not fully quantified, and solutions are neglected because with the argument, with the substantiation that it would affect operations. But sometimes it makes sense to look there anyway, if this could be a good solution, even if it affects operations. If it's small and limited, then it can make very well sense. So it's a broad bundle of challenges, of course. And I haven't yet spoken about the interfaces between the different software solutions and the different departments of the bus operator, which are also challenges as well.
Mm-hmm. Thank you very much. So I think also there's a question in the chat which goes in a similar direction. So Sayan Roy asks what disruptions one has to factor in during preparing bus schedule or system design. I don't know if you want to go into that again.
Yeah.
But yeah, please feel free to do so.
Yeah, that's also a very valid question, I think, because the very obvious example, if you have an opportunity charging scheme, that means charging at the terminal stops after each journey or after every other journey, then the question arises: what happens if the charging station fails, or what happens if the I don't know, if there's a vehicle parked at the charging station, a private car or so, that the bus cannot reach its charging station. Of course, you always have to factor in a certain buffer of energy to make sure that the bus can, with an increased energy consumption, can return back to the yard. Such kind of things. This is exactly the scenario calculation that I'm talking about. So, for example, in the simulation, switch over charging phase to see how this looks, how that will look like then, how the state of charge profile will look like, and you can then dimension the buffer knowingly about the impacts. I think that this is really important. So, what about the charging infrastructure, the availability there? What about delays? The charging state, if this charging event could it be skipped, or do we run out of energy then? So these are things that we need to answer there or become aware of.
Absolutely. And so the next question would be, what could be some of the probable ways in which funds can be attracted for e-bus projects in the cities, especially for developing countries? Yeah.
That's good question. I'm not sure if I am the right one to answer this, actually. I could imagine that maybe you at TUMIVolt have an opinion on this, but I would say that, of course, many suppliers and many manufacturers in other countries are interested in selling their products, and that this will somehow be the connection there. But I would have to say that I'm not the expert in this field.
Which is not a problem, of course. You're, I think, more focused on the simulation part, and maybe. I mean, I don't have the right answer to this myself at the moment. Just thinking about development banks who can, of course, be a good source of financing. For example, I know that the German development bank KfW financed 500 e-buses in India and in Tamil Nadu, in the state of Tamil Nadu. So this is always something cities can tap onto or tap into. But maybe moving to the next question. So how e-buses, how can e-buses be charged during power outages? And is this a challenge even in developed countries like the US? What would you answer that?
Yeah. We also had these discussions, and it actually really depends on where you look at which country. And for example, in Germany, it's as the charging or the electricity infrastructure is pretty well. The build out is quite strong. We get into a lot of discussions with the electricity networks operator, and at the end of the day, we find that the charging power required is not so super high. And now looking at outages, we have to be also consider, of course, that I don't know, for trams or so, there's also very few of such measures to be taken for outages. But we know in other countries, and maybe also larger countries with more distance need to be covered. I also think about potential storage systems for the depot to ensure the charging of the buses and availability. But of course, this is also then comes along with a lot of infrastructure efforts then, and it needs to be designed accordingly. And some also consider independent energy production there. So the same goes also for the hydrogen supply, for example, where we see then some are considering generating hydrogen from out of gas then on site as a backup solution. So there is a lot of it's a broad field and needs to be looked at individually, of course.
Mm-hmm. I see. Thank you. So coming to the next question, quite interesting as well. Should the charging stations be available only on the bus depots or in the bus depots or throughout the bus route? And also if or whether battery swapping can be an option for quick charging?
Yeah. I think that if charging, I mean, in general, you can say that charging in the depot makes sense basically in every case. But the question is, do we also need to charge at terminal stops in the city? And there the answer is that it really depends. We've seen a lot of bus operators, smaller bus operators, where maybe in more rural areas where we don't need to recharge somewhere outside the depot, we can electrify the fleet without recharging at terminal stops or in the city. When it's a high strain bus line with a high frequency and so on, and it could get difficult. It really depends also on the operations scheme. If you have peaks during the day and in terms of vehicle requirement, so if there's this camel curve, if you will, when you have a morning peak and an afternoon peak, then it could make sense to charge in the depot, because there you have time to during the day between the peaks. If you have if it's a flat curve, the number of buses over the day, the number of services over the day, then it could, and if it's a long plateau, then broad plateau, then it could make sense to recharge also at the terminal stops, for example. It really needs to be analyzed, as well as, of course, the availability of space and electricity network connection at the terminal stops or at charging hubs in the city. That needs to be considered too. And also regarding battery swapping, I would say that we have seen such projects, and we know that, for example, in China, they have these buses in for the Olympic Games there, for the shuttle services there. And we've seen such projects in Europe too, but currently there are very few left. And I think that the reason it's quite complex. It's a lot of robotic that is required to swap the batteries efficiently, and it brings along constructional challenges for the buses. I would say that electricity is basically the easiest energy carrier to distribute, and not batteries. And that is, I would say, it makes more sense, and this is what reality shows us, that to connect the vehicles to a charging station and recharge them instead of swapping batteries. That's at least what we will see here in Europe and in the US.
Thank you. Perfect. Looking at the time, I would allow maybe one last question, and then already close this webinar. But thank you very much so far. So our colleague Rohan asks, how does the operation monitoring of e-bus fleets being carried out using e-bus software? Does it require a specific e-bus plan hardware to be installed in the buses? Thank you.
Yeah. So yeah, just to make it more transparent or make it more clear. So the software for the strategic planning that I have mentioned is a standalone tool that is offline for offline planning, and it doesn't monitor the operations. It's really for the strategic system design up front to develop a transition plan and simulate operations offline. There are many different solutions for monitoring buses during operations, and yeah, there's different solutions that are available, and it's for example, in Germany, there is a working group of the German Association of Transportation Companies working on a standardized format there of the information to be taken from the bus, such as battery voltage, energy meterings, and so on. And then the ITCS system, the onboard computers there, could collect them and send it to the controlling people, the controllers there, and to the servers of the bus operator. Usually, they wanted to have it on premise, of course, and then it could be there distributed to the different planning phases and to the dispatching and so on to optimize the energy consumption there.
Great, perfect. And maybe last follow-up question, sorry, but someone asked, how can we use the e-bus plan software? Maybe quick answer to this one.
I would suggest that I leave my contact details, and then we can speak about this then after this webinar there.
Perfect. Sounds about right. Okay, thank you very much, Mr. Zinnhuber, for this great Q&A session, and of course for the presentation before. Just one last word from our side to the participants. Thank you very much for all your questions, which we all try to answer, of course. I think we did quite well. And just here you can see all the social media channels which we are active on: YouTube, Twitter, and Facebook. The Transformative Urban Mobility Initiative, so please feel free to check it out. We have a lot of material about e-buses as well. Rohan posted the link of an e-bus checklist we just produced into the chat. And with that, I'm coming to an end and would say thank you very much for tuning in, and we will see each other hopefully for the next TUMIVolt Charging Station. you very much to all of you and have a good day.
Thank you very much. Bye.
Thank you.
Thank you.